So we're in chapter 4, and let's press into it. Last time we covered a force couple, and when you have a force couple, then they can create a moment on our object. And so you talk about the moment of a couple, and that's a free vector. We could, and I hope to solve some more problems, or encourage you to solve a lot of homework problems with that, but I need to move into basically equivalent systems. So you can simplify a more complex force system, we saw that before, by having just a single resultant force. You can do the same thing for moments. So the moments, you can have an equivalent single couple moment applied to the body or object at a location, which gives it the same tendency for the body or object to rotate. Just like the equivalent force had a tendency to translate the object, the resultant moment would be for the body to rotate about 3 of the axes, just like the force translate about 3 axes or down 3 axes. So there's 2 sections of this. One is the simplification of force couple system, and then further simplification. All right, so just as I was mentioning, force, we already exposed to that some of the forces as a resultant force. Each of those forces are basically like a sliding vector. So if I had my object like this, and the force is applied right at that point on my object in that direction, well, I didn't put it right on the point, did I? Here it is. There would be no difference if it had been applied at that point on the object or that point on the object, as long as it's along that line of action. So you think about the force vector as sliding along that line of action. That's the principle of transmissibility. Okay, same with the couple moment. They are not sliding vectors, but free vectors. It's as if it could be applied at any point, at that twisting, rotating action, making it want to rotate. The force by itself makes it want to translate. So here's a problem. We have a body that looks like this. It just has a rod that comes out, it's bent, it comes out, it's bent, and it comes out and ends. So there's the rod. It has one end of the rod at the origin of my X, Y, Z coordinate system. And we have a force, F1, that's shown acting on it at this location. Another force, F2, shown as a vector acting on it in that location. And another force, F3, at the different location on this object. Now, force 2 is expressed as a vector. So it's so many newtons in the X and the Y and then the Z direction. It's hard to show it in 3D, but there you go. There's the best rendition. But there's the 3-dimensional vector, force vector for F2. The question is can you replace the force system with an equivalent force and couple moment at point O? So you want to just, the first part is easy, get that equivalent resultant force to replace those 3 individual forces. We've done this, so you would just say express F1, add it with F2, add it with F3, and that was your resultant force. What's really new to this problem is replace that force system with an equivalent also couple moment at point O, meaning that these 3 forces may make the system want to rotate, tendency to rotate around point O. So if you put that resultant force at point O, then it wouldn't want to rotate about point O because the resultant force is applied at point O. So now you're going to have to put a couple moment, a free vector. It's just a moment vector. So it's like, getting a little more abstract here, but I think we can handle it. So you're interested in getting a moment vector as a free vector, and maybe I'll put an R subscript on it saying, oh, that's my equivalent resultant couple moment applied at point O. And then it would be, okay, well, what is the moment that the force 1 generates about point O? What is the moment that the force 2 generates about point O? and a moment, that the third force, force 3, generates about 0.0. And for the systems to be equivalent, the right-hand side needs to equal to the left-hand side. Just like it did for the forces, now it does the same for the moments. All right. So let's express force 1 as a vector in ijk. So it would be 0 in the I, 0 in the j, negative 300 in the k. Units of Newton, there's a vector for force 1, right? Do you agree? Okay, how about force 2 or force 3? So it'll be 0 in the I, 200 newtons in the j, 0 in the k, newtons. And we're going to need those. So, but we can now add it up, and let's just say that we've done this before, so you can do the math on that one, and you'll get the resultant force is negative 200 in I, 700 J, and negative 600 K newtons. Okay, now the harder part. I need to get that equivalent couple moment that I'm going to call a resultant moment applied at 0.0. Well, I need to calculate what's the moment that the force 1 exerts. What is this equation? I'm just going to use R cross F. R1, F1. I'm just going to cross them. Add to it R2 cross F2. Add to it R3 cross F3. Because it's 3D and we already have some vectors represented in three-dimensional Cartesian vector form. This is a good way. So let me do this. I want to pause for a minute, and I'd like you to do this part right here. What is R1 cross F1? So you have to get R1, then you have to look at F1, maybe even set it up as a matrix, or there's another way of doing it. But can you calculate that for me? And you'll get something in the I, something in the j, something in the k. It's a vector. And the units on this will be Newton meter. Call me over when you get that part solved, okay? For 7 correct. I wish I could give you more. All right, so what people are finding is this comes in at negative 600, and 0 in the j, and 0 in the k. Now, the first person who did it, did you actually set it up in a matrix and do the determinant of that 3 by 3? Is that the way you did it? Yeah. Nope. There's more than one way to solve these problems. When you get a really complex force and a really complex displacement R, then yeah, you should rely on doing the cross product mathematically. But this one you can do using your hand, right hand, can't you? So if I look at it, this force is only in the z direction, true? It's downward. So, and it actually goes right through the axis y. If it goes right through the axis y, can it induce a moment around the y-axis? Make the object want to rotate around the y-axis? Cannot. And so right away I can tell that this part is 0. All right. Now, it's also aligned with the z-axis. So if the force is aligned with the z-axis, can it make it want to rotate around the z-axis? Nope. So this part is 0 as well. You see the logic on those two? One, the force is aligned with an axis. It can't make it rotate around that axis. The other is the force goes through the axis. It can't make it want to rotate around that axis. But the last one, it's around the x-axis. Okay. If I look at it, I use my right-hand rule, and I kind of say, okay, it's going to have to rotate around that x-axis, and the only way I can make it work is if my thumb points in the negative x direction, all right, and my finger then curls on my right hand in the correct way to make it want to rotate that way, which is, if you're looking from the positive x backwards, if you're looking that way, it's the clockwise or the negative direction. So two ways of getting that negative sign on the 600. And how did we get the 600? It's the magnitude of that force times that perpendicular distance of 2 meters. Is that the way you did it? Yeah, pretty fast that way. So that'll work for a simple force. It'll actually work for this 300 force 3. Do you see that? So let me do this. I know we can set it up in matrix form, but can you get it using kind of a scalar analysis? What is this component right here? What is R3 cross F3? What's the moment that the third force induces about the origin? All right, let's go ahead and do that. And then we'll do the hardest one, which is the second. So do this one. All right, so this works out right here to be 300 Newton meter. And then you can even just use your right-hand rule, put your thumb up in the Z, and this force right here, its line of action goes back. It makes it want to rotate in the positive sense. K. Maybe I should put the K right there. K. There you go. 0I, 0J. Now, I would encourage you to do it both ways, kind of a scalar analysis, as well as set it up with R cross F in a vector, not a vector, matrix, and do the determinant. Okay. Now the hard one, or the harder one, it's really mathematical. Just go ahead and you can use a scalar analysis if you're really good, but let's just set it up and do it with the matrix. So this one is going to be IJK. The displacement R2 is going from the origin out to this point. That would be how much in the X? 1.5 meter. I like to put the units over on the side of that row. The J, what is the J for this one? Is it 2? 2 meter out, and 0 in the K. And then for the force, F2, you have negative 200, you have positive 500, and you have negative 300, and you need to take the determinant of that to get what is that moment that the second force induces about the point O. Good? How many people can now do this on their calculator? Good. Very good. Did you already run it? Who ran it? Well, just I need one person to tell me slowly so I can write it down. What is the answer for this one?
Negative 600 I plus 450 J plus
50K. I ran out of space. Boy. And the units are Newton meter. All right. Thumbs up. Other people that ran it look good. Thank you very much. So what you would do is add those together, and so your resultant moment, right there's the answer, is applied at the point O, and now that's an equivalent system. So I can replace 3 forces that are applied at different locations on my object by a single force applied at the origin, plus the couple moment applied at that origin.
So the couple moment is
Well, this only gets more challenging. And so 4.8 may be one of the more challenging sections in this chapter for sure. And I think you can take a look. Well, what happens if you have a concurrent force system? What happens if it's a coplanar force system? What happens if it's a parallel force system? Or what happens if a wrench or a screw? Oh boy. All right, let's break this down easy. Concurrent force system. What does that mean? That all the forces go through a point. They all meet at a point. And so what you can do on a two-dimensional, it's easier to see. That's maybe not the best. I'll draw it like this. Here's a force and here's a force. Here's a line of action. Maybe I should put a vector showing the force, point of application, the head. Here's a line of action. So they are concurrent at that point. So what you can do is you can put a resultant force at that point where they all intersect, and then you don't need a couple moment. It's that simple. All right, how about a coplanar force system? What does coplanar mean? All in a single plane, just in 2D. This is real 2D. I know I just showed one there. It shows 2D, but this is truly 2D. So you can have the F of R acts at moment arm D from the point. So what you do is maybe you have your two-dimensional coordinate system, and you have a force and a force here, and they're in that plane. You can pick where you put the resultant force such that it has a correct moment arm distance to give the same moment on the object. All right. Then no independent couple moments needed. You almost need to work a problem or two. Okay. How about this force system? A parallel force system. What does that mean? Yeah, they're parallel. So now in 3D, this becomes a little more helpful. Okay, so in 3D, maybe the forces are all applied, all aligned with the y-axis. How's that? And this is my x, y, z axis. Then they induce a moment only about point around the axis z and is around the axis x, not around the axis that they're parallel with. All right. And then we're going to get to a wrench and a screw, or a screw. This is just like a screwdriver. When we get there, okay, not going to get there today, I don't think. But you ever used a screwdriver? You have to shove it in on the head of the screw. You shove it in, so you're putting a force onto the head of the screw. Once you have it shoved in, now you can twist. So it's a combination of force in as well as torque or moment. Yeah. All right. Let's solve some problems. Replace the parallel force system with an equivalent force and specify its location on the XY plane or in the XY plane. So this is a surface. This is a face. Here's a face of an object, and it's in the XZ. Did I say XY plane? Sorry, XZ plane. All right. And you have three forces: 5 kilonewton, 7 kilonewton, and an 8 kilonewton force applied. And they give you the locations by these distances where they're applied on that face. And you look at them and they're a parallel force system, true. And so they're not going to induce any moment around the y-axis, but they do make this blue shaded object want to rotate both around the x and create a tendency to rotate around the z-axis. Okay. Now, what are they asking? We want to replace that three-force system with a single force and then specify its location on the XZ plane. Maybe we come in and say, oh, let's put the single force right here, and it's going to be in that same direction, like that. And maybe its magnitude is, 35 kilonewtons, and it's located at the X of 1.8, and the Z is located at a Z of, 1.3. I just made those up. But you see what we're trying to do. We're trying to find my magnitude of that single equivalent resultant force and the location in the X where that should be applied. Maybe I put a subscript R on there saying, hey, put that resultant force at that location X, and then put that force at that location Z, and it'll be an equivalent system. So you're looking for three things, right? The magnitude of F of R, X of R, and Z sub R. So they have to have the equivalent net translational force. That would be then, we're saying that the original system is equivalent to some reduced system or simplified system. Okay, well, what was the original system? Well, I'm going to have F1 and F2 and F3, and the simplified is just one magnitude of the force. Because they're all in the J direction, I'm not going to put an I, J, K. I'm just going to sum them up. So we're going to have, let's call this one F1, this one F2, and this one F3. And so F1 is 5, and F2 is 7, and F3 is 8, and kilonewton. And so we conclude that F of R is equal to, whatever that is, 20 kilonewton. So we solve for one of the three things we need to solve for. It is that easy, but now the harder part, right? So we still have this concept of the original system and the simplified system. And this was the sum of the forces in the Y. They need to be equivalent for both. The next one will be the sum of the moments about what? The sum of the moments about the x-axis. Okay, if I look at the sum of the moments about the x-axis, force F1 produces a moment about the x-axis. I could write that equation as the magnitude of the force F1 using a scalar analysis times what? Times the height z for that force, isn't it? Isn't that my moment arm distance with respect to the x-axis? And then we have the magnitude of F2 times the distance away from it, the x-axis, which is z2, and then we have F3, z3. And what we're going to do is we're going to say, the simplified system has just a single resultant force. Hey, I already know the magnitude of that. I just calculated it. At the location z sub r. That's where it needs to be applied. So that'll tell me where it's applied on the height of that object. True? Let me pause. Let me let you solve for z sub r. When I get a few right answers, we'll move on. All right, so I'll pick it up here. I need to probably erase a bunch. I'm sorry about that because that was all in the discussion. Some students are struggling to see the dimensions, aren't you? Sorry about that. So this Z1 is going to be this distance up, and that's going to be 0.8 plus 0.8, so that's 1.6 meter. And this Z2, because this was F1, and this is our F2, which is 7 kilonewtons, and it's going to be up a distance. Let me change color a little bit. 0.8, 0.8 plus 1, 2.6. Right? Okay. And then F3 is up a Z of 0.8. And then you solve for Z sub r out of this equation, 1.63 meter. All right. In the interest of time, how about if I just talk through what is x sub r? So how did we calculate this Z sub r? What's the principle? The sum of the moments about the x-axis are equivalent. The original system and the simplified system. Now, the sum of the moments, about which axis need to be the same between the original system and the simplified system. It's around what axis? Not the x, we just did that. Is it around the y or around the z that I need to consider next?
I'm sorry, can you explain the 1.63?
Yeah, okay, I just maybe need to finish out the math then. So what we have is 5 times 1.6 plus 7 times 2.6 plus 8 times the 0.8 is equal to the 20 times the only unknown is z sub r. And now I just solve for z sub r, 1.63 meter box, done. That help? Okay. So now the sum of the moments around which axis is my next one to consider? Is it either the y or the z? About the z, isn't it? The forces are parallel with the y. They don't induce any moment about the y-axis. So the sum of the moments around the z-axis. Okay, so I'm going to have the magnitude F1 times that moment arm distance. Well, that's going to be basically in the x direction where it's applied. And for this problem, it's going to be 1.4 meter, isn't it? Yeah. So I'm going to just start putting in numbers. Come on now. So this is 5 kilonewtons times 1.4 meter. Plus, then we have F2 times that moment arm distance, x2. And so it'll be 7 kilonewton times, I should get rid of that meter there, just I know the units. X2 in this case is 2.2 plus 1.4, 3.6. And then F3 times X3, so it'll be 8 kilonewtons times, it's the same 3.6 moment arm distance. And that's equal to our 20, F of R, times X of R. X of R. We have only one unknown, solve for X of R. And when you do, you find out the X of R comes in at about 3. So that's where it should be applied. So the resultant force has a magnitude of 20 kilonewtons, and it should be applied at 3.05 in the X and 1.63 in the Z on that face. All right, let's press forward. Oh no, I'm going to run out of time. Here's more details to what we just did. So you have the original system and you have the equivalent system, the simplified system. Only one force, but at a particular location. Yep. All right, now we work this problem. We have 3 forces, this force, this force, this force, and one couple moment. Can you find the couple moment on this problem? Where is the couple moment in this problem? Right there. That's what they're showing you about that piece of information. It's a blue curved, showing a rotation, has magnitude of 1,200 units of Newton meter. And it looks like it's applied down here on my object. Okay. So I have this force, let's call it F1, applied at this location. I have F2 applied at this location, called A, point A. That's point A. And then we have F3 is 700 newtons applied at the tip down here. Those aren't given names, but that's clear where they're applied. So replace that 3 forces and 1 couple moment with a single resultant force and specify where the force acts measured from the location such that not only does it have the same tendency to make it want to translate, but it has the same tendency to make the object want to rotate. And because they say about from point A, it's the rotation about point A. That's the easiest way to approach this problem. I'm going to run out of time, so let me kind of show you the answer so you understand what we're trying to do. We're trying to take this original system and have an equivalent system where we have a single force. That force is going to have a magnitude and some sort of orientation. It's almost perfectly down, but it has a slight angle right here. So it has an X component and a Y component. And we're going to apply it at this point right here so that it has the same tendency to make the system want to rotate around point A as the original system. Make sense? It kind of, hopefully we see where we're going. So this is an equivalent or simplified system. So how do we do that? Well, the easiest is get the magnitude of f of r. You can get that as a vector entity. You just get f1 as a vector entity, f2 as a vector entity, f3 as a vector entity, and then you just add them up and you'll get so much. You'll get f of r in the xi plus f of r yj, right? And I think we can do that. That skill set was developed in chapter 2. But we want to now figure out where to apply it, and we're going to think about moving, and we'll introduce the distance that we have to move over. We'll call that x, or x of r. How far over in the positive x direction from point A do I need to apply this force? And we saw that that force was primarily downward with a little angle, if my memory is correct. You say to yourself, well, I have to have an equation that says just like this equation, the way I wrote it, the simplified system has the equivalent translational motion or translational force as the original system. Well, here is I'm going to have my r cross f, if you want to put it in vector notation for that location. So this is the r sub x, and this is my f of r, or this is, okay. Or forget the vector notation, just do the scalar notation because it's so simple to do. This one would have your downward component as well as your horizontal component. That's f of r in the x. This is downward f of r in the y. Only the f of r in the y produces a moment around point A. F of r in the x, line of action goes through point A. So you would have that this would be the magnitude f of ry, that's this right there, times x of r. That's by simplified equivalent system. What about for my original system? Well, that's a little bit of work. I decompose this force into two components. I decompose the F1 in the y and the F1 in the x. Does F1 in the x produce a moment around point A? No. Does F1 in the y? Yes. And so what we have is we have F1 in the y times that moment arm distance, which is 2 meters for that y. Can you see that? Okay. How about for the F2? It goes right through point A, doesn't it? So it just put a 0 there. The second force doesn't. And then how about for this F3? I would decompose it into two components, right? And I would say this F3 in the x doesn't induce a moment, but F3 in the y does. That magnitude of F3 in the y is 700 newtons times, look at that angle, not the sine, but the cosine of 30 degrees. And its moment arm distance is 2.5 meters. This one makes it want to rotate in the counterclockwise, where this one made it want to rotate, in the clockwise. This one made it want to rotate in the counterclockwise, right? Well, if I'm going to be adding these and subtracting them, let's pick a direction which is going to be my positive. Let's say that this is the positive counterclockwise. Hence, I need to have a negative sign. It wants to rotate not in the counterclockwise, but the clockwise. And then we add our couple moment of 1200 Newton meter. I look at the way it wants to rotate. I make it consistent with my equation. So I'm going to end up putting a negative sign right there. Make sense? All right. So I'm going to have to draw it to a conclusion here. But there is the solution worked out in more detail. And the magnitude, the angle, and the offset. Thank you for your attention.